Indexed families of sets, Part 2, doubly indexed families. For our course, this is an extra credit material. We're going to define doubly indexed families of sets. These are going to be families which are indexed by two indexes. I'm choosing an index S from the set capital S and an index T from the set capital T. The members of the family are indexed by such two indexes. Here's an example. I'm defining a set X indexed by two numbers M and N. The set consists of natural numbers which are smaller than the product M times N. And now I'm letting M to be a member of the set with 1 and 2, and N to be a member of the set with 1, 2, and 3. The resulting family of sets has 6 members. They are all listed in this chart, and it is a doubly indexed family of sets. Another example, the set X is indexed by indexes P and N. This is how it is defined, and I'm letting P to be any prime number and N being any natural number. This is a doubly indexed family of sets, and one of its members, with the member with indexes 3 and 4, consists of multiples of 3 starting from 15. For a doubly indexed family of sets, we want to define the operations of union and intersection. So consider a doubly indexed family such as this, and now notice that if I fix the index t, if I take a particular value of the index t, then I'm dealing with a singly indexed family. It is indexed just by s, because t is constant. And for such a singly indexed family, I know what union means. And such a union can be formed for any fixed t. So with this in mind, the union of a doubly indexed family X sub st with S in capital S and T in capital T, the union on the first index is denoted in this way, and it is obtained by taking unions of singly indexed families for any fixed value of t. And similarly, we define intersections of doubly indexed families. In the case of intersections, you expect that it will be required that the set of indexes is non-empty. Feel free to pause the video and read everything on this slide. So we have defined the union on the first index, the intersection on the first index. You expect that we can perform unions and intersections on the second index, and the definitions are similar. They are given on this slide. Feel free to pause the video to read the entire content. Here's an example. I'm considering two sets of indexes. S contains 1 and 2, T contains 7, 8 and 9. I'm going to consider a family of doubly indexed family of sets indexed a doubly indexed family of sets over these two sets. So the family is going to have 6 members, and I'm not going to specify any particular values for these sets. We'll be forming unions and intersections, but in order to do so, let me introduce some auxiliary notation. T7 will be the union of this column, X17 union X27. T8 is going to be the union of this column. T9 is going to be the union of this column. And S1 is going to be the union of the first row. S2 is going to be the union of the items in the second row. And now, what is the union of this doubly indexed family on the first index? Union with S in capital S. For every T in capital T, we are treating the little t as fixed, and we are forming the union of the singly indexed family on S in capital S. This union is equal to T sub T. So the result of taking this union is the singly indexed family T sub T with T in capital T. Similarly, if I take the union of this doubly indexed family on the second index, I will get the singly indexed family S sub S with S in capital S. I'm going to continue the same example. This part of the slide is just a repetition of what was on the previous slide, and now our task is to work out what it means that X is a member of the intersection with T in capital T of the union with S in capital S of X sub ST. First, we will work on this expression from the inside, and the union which I highlighted, as we already figured out, is T sub T. So we are working now with the intersection of T sub T for every T in capital T. And this means we are dealing with the intersection of T7, T8 and T9. And then expanding what T7 is, we write this. T8 expands this way, T9 expands this way. So we can conclude that X is a member of this kind of intersection of unions if and only if for every T in capital T, there exists an S in capital S, such that X is a member of the component X sub ST. And I'm noticing that there are some little typographical errors on this slide. This comma shouldn't be here. This comma shouldn't be here. This comma shouldn't be here. So please notice we established that X is a member of the intersection of unions of X sub ST, if and only if for every T in capital T there exists S in capital S, such that X is a member of the X sub ST. Notice that the intersection corresponds in some way to the universal quantifier. Union corresponds in some way to the existential quantifier. And we'll see more of such relations in the next proposition, in the next fact. So what we established so far is listed here in the item 8, but other arrangements of unions and intersections are explored excuse me, in the other points. And again, notice that the union corresponds to the existential quantifier, the intersection corresponds to the universal quantifier. From this fact, we immediately obtain this corollary. When we take unions of a doubly indexed family of sets, the order in which we specify the union operations doesn't matter. Here we actually start with the union over with T in capital T, and then we follow with the union with S in capital S. On the right hand side of this equality we reverse the order of the unions, and the two values are equal. How do we know this? The unions of this kind are explored in points 1 and 2 of the fact, and they are equivalent to expressions involving existential quantifiers. From logic we know that when we write expressions with existential quantifiers, we can switch the order of the two existential quantifiers without affecting the truth value of the expression. By this method we obtain the equality. And similarly we can switch the order of intersections. On this occasion, let us introduce a slightly simplified notation. In cases when we perform unions over the same, two unions over the same set. Please notice S is in T and T is in T. When we are dealing with unions of this kind, the union can be written as the union with S and T in capital T, and similarly for intersections. In this proposition we are considering results of applying an intersection and a union operation to a doubly indexed family of sets, and we are actually applying these unions and intersections in all possible ways. So intersection first, union second, or union first, intersection second, or this is the result of applying the two unions, union with J in capital J and union with I in capital I. Please notice that A sub ij is a doubly indexed family of sets. When I apply my first operation, such as an intersection, the result is a singly indexed family of sets. And then applying the next operation produces a set. So doubly indexed family, singly indexed family, and then just a set. And the diagram shows inclusions which hold between the resulting sets. In this proposition, I'm considering a doubly indexed family where both index sets are the same. I ranges over capital I and little j ranges over capital I. So this is stated here. I cannot highlight, but the two index sets are the same. And again, I will be applying unions and intersections in all possible ways and looking for the inclusions among the resulting sets. The diagram is similar to that from the previous proposition, but it also contains these items. Let me go back to the previous one for a quick look. Right. And now the new one. These are sets which we couldn't form in the previous setting, but now that the two sets are the same, the two index sets are the same, we can form this kind of intersection. And we are going to compare this with the situation with universal quantifiers. So here is the same diagram again, and below I'm presenting a diagram concerning quantifiers. So the top part of this diagram says that there is an implication between quantified formulas as you see them. Please feel free to pause the video and make comparisons to see the full analogy between set operations and quantifiers. Now we will consider the inclusion and the implication on the top of the two diagrams on the previous slide. And here they are. This was the inclusion on the top of the diagram in the upper part of the slide. This was the implication on the top of the diagram in the lower part of the slide. Let us notice that there is a similar statement concerning big disjunctions and conjunctions And then we can explore what this statement means in a particular case when the index set I consists of numbers 1 and 2, and index set J contains numbers 7, 8, and 9. In such a case, the statement concerning big disjunctions and conjunctions translates into this formula. And now, in order to read this easier, I'm going to rename the components of this formula, and this is what we obtain. And also, let us look at a particular case of this statement for particular sets of indexes. The statement translates into this, but it is easier to read if we rename the variables, and then we obtain the following. I would like to propose the following exercise. Show that converse implications and reverse inclusions do not hold.